Welcome to this lecture series in linear algebra. In this lecture, we will look at two new concepts, which are about geometric and algebraic multiplicity of eigenpolynomials. And let us recall the relevant concepts. So we have these standard notions, eigenvalues, eigenvectors, and, well, generalized eigenvectors, which we talked about. So these are the standard terminologies, and in the previous lecture we saw the corresponding generalizations. So these are all non-standard terminologies. I invented these names just for my purpose. It is possible that in the literature somewhere the notions have some other standard names, but I'm not aware. So the generalization of eigenvalues was eigenpolynomials. Just like eigenvalues are the roots of minimal polynomial, eigenpolynomials are the irreducible factors of the minimal polynomial. So every eigenvalue can be thought of as an eigenpolynomial. If lambda is an eigenvalue, the corresponding eigenpolynomial is x minus lambda. Okay. Then the corresponding generalization of eigenvectors is polyeigenvectors, a bad name, but what can I do? So suppose we have an eigenpolynomial px, then a vector v is called a polyeigenvector if pt kills v, if v lies in the kernel of pt. So of course everything is in the context where t is an endomorphism on a finite dimensional vector space v, and the base field is, let's say, f. Okay, and then we had this notion of generalized eigenvectors. So if lambda is an eigenvalue, then v is a generalized eigenvector corresponding to lambda if this thing kills v, meaning when you apply v to it, you get 0. And generalized polyeigenvectors are defined as follows. If px is an eigenpolynomial, then v is a generalized polyeigenvector corresponding to px if pt to the power dim v kills v. So you should be able to now you should be able to see that these are actually genuine generalizations. Okay, and again, these are non-standard terminologies and these are standard terminologies. All right, so let us now proceed. So first we will define the geometric multiplicity of an eigenvalue. So again, our setting is the same. T is an endomorphism on a vector space V. The base field is f, which we suppress. And as usual, everything is finite dimensional. Now suppose lambda is an eigenvalue of t. Then the geometric multiplicity of lambda is defined as, notationally it is this. You emphasize the endomorphism that you're working with. You may also want to emphasize the vector space V, and you can include that in the notation somewhere. And lambda is also emphasized because it depends on which eigenvalue we are talking about. So gamma, I have chosen the symbol gamma. This symbol is also non-standard. I've chosen the symbol gamma because G for gamma and G for geometric. Okay, so the geometric multiplicity of lambda is defined as this number, which is the dimension of the kernel of t minus lambda I. So it's the, okay, so first you consider all the eigenvectors corresponding to lambda, which is this space. You take its dimension, that is the multiplicity, the geometric multiplicity of lambda. Ignore this figure for the moment. This is the definition. Let us look at an example, and this is a fairly easy concept to grasp, so I don't think I need to say too much about it. So let's just see an example. So define this endomorphism on R3. So the definition is it takes the vector x1, x2, x3, meaning whose coordinates are x1, x2, x3, to this element x1 plus x3 minus x2, and the rest is the same. Okay, so then you can see that 1 is an eigenvalue. Why is that? Because TE1 is E1. E1, again, recall, is the standard basis vector 1, 0, 0. This is E1. And you can immediately see that T fixes E1, and therefore 1 is an eigenvalue of T. Now we are asking, what are all the vectors, or what is the dimension of the space of all the eigenvectors corresponding to 1. And now you may look at this picture. What I'm trying to draw here is this plane which passes through this entire x1 axis. So t fixes E1, so it will fix everything on this line. So the space, the subspace of all the eigenvectors corresponding to 1 should contain, or must contain this line. And it also has this vector, E2 plus E3. So you can also check that this is also fixed by t, and hence this is also an eigenvector corresponding to the eigenvalue 1. So that's that. Let me just see if I have not made a mistake. Yeah, this is fine. So the space of all the eigenvectors corresponding to 1 must also contain this line. So it contains that line and this line, and hence it contains the plane spanned by that. And a matter of computation will show you that nothing outside this is in the set of all the eigenvectors corresponding to 1. So this is the space of all the eigenvectors corresponding to 1, and hence the geometric multiplicity of the eigenvalue 1 with respect to the endomorphism t is 2. Gamma 1 comma t, or 1 colon t, is this dimension, which is 2. Okay, so please make the computation to convince yourselves that this is actually the case. I have explained geometrically why that is the case. Okay, so now let's move on. Now we will define what is called the algebraic multiplicity of an eigenvalue. Again, we have an endomorphism t on a vector space V. We have an eigenvalue of t. The algebraic multiplicity of lambda is defined as this symbol. So I have chosen alpha because A for alpha and A for algebraic. And the rest of the artifacts are as they were in the previous slide. And we define this as the dimension of the kernel of that guy. And this may be a little bit tricky to understand intuitively, but let me try to explain. So for the sake of understanding what is going on here is you take lambda is 0. Suppose we are talking about the eigenvalue 0, and let us try to understand intuitively what is meant by the algebraic multiplicity of lambda. So by definition, it is this. It is that guy. And the point is that the kernel of t may be strictly contained in the kernel of t square. So there may be points which are not in the kernel of t, but when you apply t to them, they fall in the kernel of t. So you may have, let's say this is the kernel of t. There may be a point which is not getting killed by t, meaning it is not on this line. But when you apply t to it, it comes into this line, so that when you again apply t, it dies. So there may be vectors for which t square v is 0, but tv is non-zero. So those things are also now counted. They also account for this number. And this may continue up until the dimension of v. So as we learned way earlier, that even if you write a higher number here, doesn't change anything. This is the saturation. I think I called it the kernel saturation lemma or something. So even if you write a higher number here, it will not change this thing. Okay, so that's the intuitive meaning of algebraic multiplicity. And now let us look at a very simple example. So this time we will have an endomorphism on R2. We define it via the following equations. It fixes E1, but it takes E2 to that thing. And it would be a good idea for you to draw a picture simultaneously as you're taking notes. So then lambda is equal to 1 is an eigenvalue. Why is that an eigenvalue? Simply because of that equation. So that is an eigenvalue But if you just try to see if there are things in the kernel of this guy which are not in the kernel of t minus lambda I. So before we continue, let's just nail down the geometric multiplicity. So the geometric multiplicity of lambda, which is equal to 1, this is equal to 1. It's a matter of pure computation. Just try to see what are all the vectors which are fixed by t. The description of t is available here, so you can just immediately do a computation and verify this. So this, I meant to write gamma, not alpha. This is gamma. So that is the geometric multiplicity. But if you compute this thing for E2, you will see that this is equal to, what is this? This is equal to that, which is same as that, which is 0. So this guy kills E2, and this guy of course kills E1, because even a smaller power of t minus I kills E1. So this guy kills everything, because it is killing both the basis vectors of R2. So everything in R2 is in the kernel of this guy, and hence the algebraic multiplicity of 1 is 2. So this is a genuine example where the geometric and algebraic multiplicities of a given eigenvalue are different. Okay. So now we will go to the generalizations of both these concepts, the generalization of the geometric multiplicity and the algebraic multiplicity for eigenpolynomials rather than eigenvalues. Okay, so how do we define geometric multiplicity of an eigenpolynomial? You fix an endomorphism T on a vector space V, Px be an eigenpolynomial of T. Then the geometric multiplicity of Px is defined as, you can easily guess, kernel of Pt. That's it. Sorry, dimension kernel Pt. Kernel Pt would be not a number. That's what the geometric multiplicity is. And since Px is a polynomial, if it were a degree 1 polynomial, then this notion is no different than that of the geometric multiplicity of an eigenvalue. But if it is a higher degree polynomial, then it is difficult to intuitively or visually see what is going on. However, this is a very useful concept. So let's just see a solid example where we can appreciate this. So this is an example which we have seen earlier when we were discussing eigenpolynomials. So let V be this 4-dimensional vector space and fix a basis, which we will name like this. You can take the standard basis, but I'm just naming it that way. So define an endomorphism on R4 by the following equations. Or maybe let me write it the other way. So and TV0 is U1 plus V1. Right. So we have that. And then we have already computed this, that the minimal polynomial of this endomorphism is x square plus x plus 1 whole square. So this is the only eigenpolynomial of T. This is an irreducible polynomial over R, so this is the only eigenpolynomial of T. Right, and let us call it Px. Okay, and the geometric multiplicity of this guy is 2. And that is just a matter of computation. So you know what the endomorphism exactly is, because what is Pt? Pt is t square plus t plus identity. And you just have to compute what are all the vectors that are killed by this guy, take the dimension of those, and that's it. And you'll see that it is equal to 2. I don't know what else I can say about this, because it's very difficult to visualize the endomorphism corresponding to this. I don't know how to visualize Pt. I mean, you can visualize Pt once you compute the matrix representation of Pt, maybe. But anyway, things in R4 are not very amenable to visualization. Alright, so that's the geometric multiplicity of an eigenpolynomial. And now we will talk about the algebraic multiplicity of an eigenpolynomial. So in fact, I've written everything here, unfortunately. Fix an endomorphism T on a vector space V, Px be an eigenpolynomial of T. The algebraic multiplicity of Px is defined as that. So the notation is this, and it is the dimension of the kernel of Pt to the power dimension of V. So you should be able to draw a parallel between the notion of algebraic multiplicity for an eigenvalue and that of an eigenpolynomial. Okay, and this should be clear because here we are taking the kernel of a bigger thing. When we were talking about geometric multiplicity, this was replaced by the number 1. So this inequality is trivially true. Okay, and let us just kind of repeat the previous example here and see what happens. So let me copy things. Right, so this is just like in the previous one, but if you now compute the algebraic multiplicity of P, that will be 4 because, well, one way to see it is that Pt square kills everything because the square of Px is the minimal polynomial of T. So Pt square kills everything, and hence the dimension of the kernel of Pt square is the dimension of the domain space, which is 4. So the algebraic multiplicity of the eigenpolynomial Px is 4. So the geometric multiplicity and algebraic multiplicity here also are different. Now there is no necessity for these two to be different. In special examples, in fact, maybe not in fact most of the times, but in many cases, the algebraic and geometric multiplicity may be equal. For instance, if you take any diagonalizable operator, you will see that the algebraic and geometric multiplicities will be the same. And that is a simple exercise. Okay, so yeah, I think this is all that I wanted to say. So as usual, like, comment, share, subscribe, and I will see you next time.